Let us now go through a few specific examples of how we can analyze the type of a critical point. Right. So my first example is about critical points of the system of differential equations. So notice that we already saw this example in the last lecture, and the critical points are of the type 0 and 2 pi n, and I'm sorry, not 2 pi n. So here x can be 2 pi n and y has to be 0. So these were center points. And if it is pi plus 2 pi n and 0, these were saddle points. We found it in the last lecture by computing the trajectories and plotting the phase portrait. So now let us see how we can figure it out from the Jacobi metrics. So first we need the Jacobi metrics, which means we compute both entries. So that's the first entry, that's the second entry. So we need to compute them with respect to both x1 and x2. So maybe let me just do it very quickly. So here I'm going to use x for x1 and y for x2, right? So the system of differential equations is x dot is y, and y dot is, well, dot means d over dt, minus sine x. Now, when I calculate the Jacobi metrics, so here in the first entry is, I need to differentiate the first equation with respect to x, and it depends on y, so it's just 0. So then here I need to differentiate with respect to y. So dy is 1, right? The entry in the second row, first column, is derivative of the second equation with respect to x. So it's going to be minus cos x. And then I need to differentiate with respect to y, so it's going to be 0. So this is how I can get the Jacobi metrics. Right? And the first critical point is 0, 0. So letting x and y to be 0, I'm going to get this Jacobi metrics. So this is the matrix of the linearized system. Well, and computing its important characteristics, so which are the determinant, the trace, and the discriminant of the characteristic polynomial. So this d is the discriminant of the characteristic polynomial. Okay. So we see that the linearized system has a center at the origin. Now, the problem with this is that our celebrated theorem does not give us a definite answer, right? So if the linearized system has a center point at the origin, it means that the original nonlinear system may have a center, or it may have a spiral point at the origins. Well, so we don't know. Okay, so let's do the other critical point. So the other critical point is pi 0. Then again, we substitute pi 0 to the matrix, to the Jacobi matrix, and then we get this this matrix, and the determinant is negative. So since the determinant is negative, immediately it means that the linearized system has a saddle point at the origin. Okay, so then the nonlinear system has a saddle point too, which means that we kind of find out. So notice that here we actually know that the critical point 0, 0 happens to be a center point. Is just that it's not because of the theorem that we just learned, but because we managed to compute trajectories in the last lecture. And we plotted the phase portrait, and we saw that trajectories are actually, they encircle the critical point, so which means it is a center point. But what is good due to the theorem that we just featured is that we theoretically proved that the critical point at pi 0 is actually a saddle point. So now we have a precise, a rigorous theoretical proof of the fact that this is unstable. Okay, so here is another example. So it also comes from the previous lecture. So recall that in the last lecture, when we did this, the critical points were still 2 pi n and 0, and another series of critical points is pi plus 2 pi n 0. And then from plotting the phase portrait, we kind of saw that this should be a spiral sink. As far as I remember, spiral sink. And these are saddle points. But we could not compute the trajectories. So we just guessed the answer by staring at the phase portrait. So let us see if we can get this result rigorously by applying the theorem. Right. So the first critical point is 0, 0. Then here is the matrix of the linearized system. And now the determinant of this matrix is positive, is plus 1. The trace is negative, and the discriminant of the characteristic polynomial is negative. So if the discriminant of the characteristic polynomial is negative, it means that the eigenvalues are complex. But since the trace is negative, it means that the sum of the eigenvalues is negative. So the real part of each eigenvalue is negative. So therefore, it is stable. Right? So it is a spiral sink. So good. Now we are able to prove it rigorously. So the second critical point is pi 0, and then here is the linearized system. So its matrix is just a Jacobian matrix evaluated at the critical point, and its determinant happens to be negative, so it is a saddle point. So in other words, now we proved it rigorously that we have a series of spiral sinks and a series of saddle points. So here is my next example. It is the purpose of this example is to relate types of critical points for in differential equations to types of critical points in calculus 3, right? So suppose that we have a function of two variables, and consider the following system of ordinary differential equations. So you if it is hard for you to understand this, maybe you can imagine any specific function of two variables, like, I don't know, cosine of x plus y. But if you have any specific functions on function of two variables, you can differentiate it with respect to x, differentiate it with respect to y. Then you will get two expressions, one in x, one in y. Then you can make a system of autonomous differential equations out of it. Right? But then if you find the Jacobi matrix of the resultant system of the differential equations, you will see that the Jacobi matrix of the system of differential equations is nothing else but the Hessian matrix of the original function of two variables. Right? So, which means that the critical points of the system of differential equations are actually the same as critical points of the function understood in terms of calculus 3. And you can even relate types of critical points. I suggest that you do this. You solve this very useful exercise and share your ideas as comments to these YouTube videos. But let me just show you what it means for a specific equation. Right. So here, if you want to do a specific equation, then you will get dx dt equals is x squared minus 1. Right, so dy dt is going to be the derivative of phi with respect to y is y. And then when you solve, when you find critical points, right? So if dx dt is 0, then x squared minus 1 is 0. So x is plus minus 1. If dy dt is 0, then y is just 0. So we have two critical points, 1, 0, and minus 1, 0. And then you can plot the corresponding a face portrait, and then you will see that 1 0 is a nodal source, and -1 0 is a saddle point. Well, and these points correspond to a point of local minimum and a saddle point of the um, original function of two variables understood in terms of calculus 3. Right? So here is you can try to continue, and you can try to play with arbitrary functions phi of x and y to figure out what is the general rule here. All right, so here is a little quiz for you.